Okay, let's dive right into this. I want you to picture something. Imagine you're sitting in your Cambridge physics exam hall. The clock at the front of the room is relentlessly ticking down. You turn the page, and there it is, staring right back at you. A massive, multi-part extended response question on the kinetic model of matter. Now, did you know that gas pressure, particle motion, and Brownian motion account for a staggering 15% of the total marks in the Cambridge Physics 0625 examination syllabus? And honestly, it's not just the 0625. This heavily features in the 0651, 0652, 5054, and 9702 papers as well. Listen to me, that 15%, that is literally the difference between an average grade and absolute top-tier exam mastery. It's the difference between scraping by and totally dominating the paper. Now take two typical students taking this exact exam right now. Let's call them Alex and Sam. Alex is what I like to call the fact dumper. You know the type, right? Overloading the page with every single raw physics fact they can possibly remember, but providing absolutely zero analytical structure. The result? A literal sea of red pen from the examiner. Sam, on the other hand, is the rusher. Sam panics, completely skips over the command words, and entirely misses the actual requirements of the question. Again, red marks everywhere. Neither of them is thinking like a chess grandmaster. They're just reacting to the board. But today in this explainer, we are going to completely change that approach. We are going to train you to anticipate the examiner's next mental move 5 steps ahead.
Welcome to this exclusive masterclass explainer. Today, we are cracking open the examiner's playbook. We are decoding exactly what those principal examiners are desperately looking for when they sit down to mark your papers. You and I are going to transform those red pen corrections into green check marks right before your very eyes. You see, the theoretical architecture of gas pressure and Brownian motion, well, it isn't just about memorizing some textbook facts. Not at all. It entirely rests on your ability to establish precise definitions, form rock-solid causal relationships, and seamlessly integrate your knowledge with other syllabus areas. I've read the principal examiner reports, and they explicitly highlight that candidates who understand these cross-topic connections are the ones who achieve significantly higher marks. It is all about how you structure your underlying logic. So what we're doing right now is building your physics success blueprint. By the time we're done, every single time you see a question on the kinetic particle model, you will know exactly which move to play.
All right, let's quickly run through our agenda for today. First, we just covered the 15% challenge. Next up, we'll build our core foundations. Then we move into technical methodology, followed by critical evaluation. And finally, we'll hit the examiner warnings so you can avoid those classic traps. Let's get straight into section 2, core foundations and mastering the terminology. Okay, think of your physics knowledge like a massive skyscraper. If the foundation, meaning your basic definitions, is weak or shaky, the entire structure is going to collapse under the pressure of a high-mark extended response question. The assessment framework for Cambridge Physics heavily, and I mean heavily, prioritizes precise language. When examiners read your paper, they are rapidly scanning for very specific keywords. If those keywords are missing, honestly, it doesn't matter how beautifully written your paragraph is, you will lose the marks. So, how do we construct these bulletproof foundational definitions? Let's start with gas pressure. Whatever you do, do not just write particles hit things. That is exactly what Alex the fact dumper did, and Alex lost the marks. Instead, I want you to use a visual story method in your mind right now. Close your eyes if you have to. Imagine a rigid, perfectly closed container. Inside that box, there are billions of microscopic gas particles, and they are in continuous random motion. They are zipping around, constantly colliding with the internal walls of the container. Now pay attention, because here is the exact phrase that earns you the marks. Every time a particle collides with the wall, it experiences a change in momentum, which exerts a force on the wall. Pressure is the total force exerted by these collisions per unit area of the surface. Did you catch that? Force per unit area, change in momentum, collisions with surfaces. When you physically link that random particle motion directly to these mechanical concepts, you show the examiner you have deep analytical understanding, not just some rote memorization you crammed the night before.
And this perfectly illustrates our next core definition, Brownian motion. Now, why do so many students find the distinction between these key terminologies so impossibly hard? Well, it's actually simple. It's because they completely confuse the macroscopic with the microscopic. Let me clear this up. Brownian motion is the erratic, random, zigzag movement of relatively large, visible particles. Think of things you can actually see under a basic microscope, like pollen grains suspended in water or smoke particles floating in the air. But here is the ultimate secret to grabbing top marks. You must explicitly state why they are moving like that. They are moving because they are being constantly bombarded by massive numbers of much smaller, invisible, extremely fast-moving particles, like air or water molecules. Brownian motion is the ultimate bridge between abstract physics and visible evidence. It's the actual visual proof that the kinetic particle model is real. When you write down that the random bombardment from unseen molecules causes the visible particles to dance erratically, you secure maximum points. Before we continue, subscribe to our YouTube channel Ace the Exams at @aceexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, this is where we introduce the Peel framework. Point, evidence, explanation, link. Top students automatically structure their physics answers by first establishing the core terminology before diving into their complex explanations. Let's say a question asks how temperature affects gas pressure. Your very first move, your point, is to precisely define what gas pressure actually is using that particle collision model we just went over. Then, your evidence is the increased temperature provided in the question. Your explanation dives into how a higher temperature means a higher average kinetic energy, which logically leads to more frequent and much more forceful collisions with the walls. And finally, your link ties it all back directly to the resulting increased force per unit area. Define before you describe. If you do this, you literally take control of the grading rubric.
Moving right along to Section 3, Technical Methodology and the Method Marks Strategy. So, the conceptual framework for tackling these exam questions draws heavily on systematic analysis. You have to realize that the examiner isn't just hunting for a magic final number scrolled at the bottom of the page. They are evaluating your entire procedural framework. You can literally guarantee yourself marks by simply formatting your thought process correctly on the paper. This 4-step framework is the exact remedy for Sam, our rushing student who completely missed the command words. Step 1, deconstruct the question. Before you do any math, highlight the command word. Is it describe? Is it explain? Or is it calculate? Look, if it says explain, you absolutely must provide the underlying why, not just the what. Step 2, extract the relevant data from the scenario and list it out. Step 3, execute with clear notation. This right here is where the method mark strategy really shines. Write down the algebraic formula before you plug in a single number. Show your working line by line. Why? Because if you make a silly calculator error at the very end, but your formula and your substitutions are spot on, the examiner will still award you method marks for the process. And step 4, verify the results. Take a step back. Does your final answer actually make logical sense in the context of the kinetic model?
So the crucial takeaway here is professional execution. The Cambridge syllabus explicitly states that practical application in physics develops professional skills. Applying correct formats using the appropriate number of significant figures, explicitly stating your units at the end of a calculation. Guys, these aren't just polite suggestions, they are strict, non-negotiable requirements in the assessment framework. If you flawlessly calculate the pressure but forget to write pascals or newtons per square meter at the end, you are literally throwing away hard-earned marks. Treat your exam paper like a professional engineering report. Be precise, be methodical, and leave absolutely no ambiguity for the examiner to have to guess what you meant. Make it easy for them to give you the grade. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @aceexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's jump into Section 4, Critical Evaluation and Thinking Like a Top Scorer.
Now, this is the exact moment where we separate the A grades from the A stars. Top-scoring candidates constantly demonstrate evaluative thinking. They don't just blindly solve equations, they question assumptions, they consider different perspectives, and they fiercely justify their decisions with hard physical evidence. Let's run challenge 1 of our interactive workshop right now to contrast superficial breadth with analytical depth. Imagine a complex physics chart on your screen. It shows gas pressure increasing as volume decreases while keeping a constant temperature. We all know it, it's Boyle's law. I'm giving you a 60-second mental timer right now. Tick-tock. A superficial student scans that chart, shrugs, and writes, the line goes up when the other goes down. Boom, that is superficial breadth. 0 marks for explanation. But a candidate with analytical depth, they extract the core trend using the kinetic model. They write, as the volume halves, the particle density doubles. This leads to twice as many collisions per second with the container walls, therefore doubling the force per unit area, hence doubling the pressure, assuming average kinetic energy remains constant. Do you see the difference there? It's night and day. Analytical depth uses the actual physical mechanics to justify the data on the page.
Let's tackle challenge 2, find the flaw. I'm going to read you a sample paragraph from a real student's exam, and I want you to spot the mistake. Ready? When the gas is heated, the particles expand and take up more space, so the pressure increases. Okay, where is the flaw? I'll give you a moment to think. Got it. The fatal flaw is saying the particles expand. Listen to me carefully. Particles themselves do not expand.
The space between them increases as they move faster and push outward. This brings us right back to the deconstruct, solve, evaluate framework. When you solve systematically, you must evaluate for reasonableness. Are you accidentally breaking fundamental laws of physics in your English explanation? High marks are always hidden in this final step of checking your results for logical consistency. All right, for Challenge 3, our speed writing drill. Imagine you have a 30-second timer to mentally write one perfect Peel paragraph based on this 3-word concept: extract, interpret, conclude. Your data interpretation skills are absolutely critical here. When you're faced with a table showing temperature and pressure readings, you must first extract the raw data directly from the text. Then, interpret the underlying relationship, perhaps demonstrating that pressure is directly proportional to absolute temperature. And finally, draw a solid, evidence-based conclusion. If you just jump to the end and write down the final conclusion without showing the examiner the extracted data and your interpretation steps, you are skipping the rungs on the ladder. And if you skip the rungs, you will fall short of the total available marks. Every single time. Let's bring it home with Section 5, Examiner Warnings and Avoiding the Classic Traps. So, my team and I have scoured the Cambridge Principal Examiner reports for these specific syllabus codes to find the exact places where candidates just hemorrhage marks year after year. The entire assessment framework is practically designed to catch students who rely on rote memorization without contextual understanding. By anticipating these pitfalls, you are actively employing that chess grandmaster strategy. You know exactly what the traps are set on the board, and you are simply going to step right around them. Here are the top 3 mistakes explicitly cited by senior examiners. Number 1, using the wrong approach for the context. This happens when a question asks specifically about Brownian motion and a panicked student starts rambling about convection currents. Number 2, formatting and presentation errors. I'm talking about scrawled, completely illegible working outs or forgetting your units altogether. The examiner physically cannot award you marks if they cannot read your logic. Number 3, and pay attention because this is the biggest one of all, non-specific generic answers. This means giving a highly theoretical, textbook answer about gas pressure when the question specifically asked you about the pressure inside a car tire on a hot summer day. You must apply the theory to the specific context provided in the prompt. Do not just copy-paste your textbook onto the exam paper. So the absolutely crucial point is captured perfectly in this massive examiner alert. The Principal Examiner report literally states, and I quote, "Candidates consistently confuse key terminology. Always define terms before using them in extended responses." Let that sink in. This is the ultimate authoritative rule to cement everything we have learned in this explainer today. If you are talking about pressure, define it as force per unit area due to particle collisions. If you are talking about Brownian motion, clearly define it as visible particles being moved by invisible molecules. Never, ever assume the examiner knows what you mean. Prove it to them on the paper. So I leave you with this question. Will you rely on raw facts like Alex, or will you use the examiner's playbook to secure your 15%? We've covered the Peel framework, we've locked down the method mark strategy, and we've exposed the critical traps you absolutely must avoid. As you look at your next past paper, ask yourself, are you just dumping facts, or are you thinking 5 moves ahead like a grandmaster? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.